So instead of having to draw or to be able to draw a 3D structure, we use straight lines, hashed lines, and wedges. So the dash and the wedges help us to see which direction that the molecule, or the atom is going. So for linear, trigonal, planar, and bent, we don't need a dash or a wedge because those atoms are just going either straight to the side or down. So we don't need wedges and dashes on that one, or those three. But for tetrahedral and trigonal pyramidal, we do. So the straight lines, again, just mean it's either going straight up, straight to the side. But the wedge shows that that atom is coming out of the paper, so it's coming towards you. And then the dash shows that that atom is going behind the paper. So it just gives us a better idea of the 3D look of the molecule. So last chapter we talked about some different periodic trends. We have one more to talk about. It's called electronegativity, and it actually goes along with ionization energy. But electronegativity is just the ability of an atom to attract electrons. So you can see from the chart here, those are the actual electronegativity numbers for those atoms. And fluorine has the highest electronegativity number, so at 4. And then oxygen and chlorine and nitrogen are all high up there as well. So the trend is that the electronegativity increases from left to right, and going across the period, and it decreases going down the group. So electronegativity, again, it tells us, who wants the electron more. So if it has a higher electronegativity number, it's going to pull the electron to itself. So here we have HCl, and hydrogen has an electronegativity of 2.1. Chlorine has an electronegativity of 3. So that means chlorine wants the hydrogen or the electron more than hydrogen does. So what happens is the electrons shift towards chlorine, and it creates a partial positive and a partial negative. So that's what those symbols are. So partial negative on the chlorine side, partial positive on the hydrogen side. And anytime we have a partial negative and a partial positive, we get something called the dipole. So the red arrow represents the dipole. So it just shows us what direction the electrons are going. Anytime we have partial negative, partial positive, we have that dipole. We also have what's called a polar bond. So whenever somebody's pulling the electrons to themselves and the electrons are being shared unequally, then we have a polar bond. So the way we know that we have a polar bond is by looking at the difference of the electronegativities. So here, for this one, we have 3 minus 2.1. So 3 minus 2.1 would give us an overall difference of 0.9. So anything between 0.5 and 2 means we have a polar bond. So since the difference is 0.9, that shows us we do have a polar bond. Okay, if our difference in electronegativities is 4 or less, and that shows we have a nonpolar bond. So that means that the electrons are being shared equally. So here with the two chlorines, they obviously have the exact same electronegativities. So our difference would be 0. So the electrons are being shared equally. And then anything electronegativity of 1.9 or greater shows us that we have an ionic bond. So that means that the difference is so great that one of the atoms is able to just completely pull the electron away from the other atom. So that's what happens here between chlorine and sodium. Chlorine is able to pull sodium's electron completely off and form an ionic bond. So here's kind of the scale. So anything less than 0.4 is nonpolar. Electrons are shared equally. Anything between 0.4 and 2. So 2 is fine. I know the slide before said 1.9. But that's a polar bond, and the electrons are shared unequally. And then anything above 2 is considered an ionic bond. So again, those numbers just represent the electronegativity difference. So all we have to do is just look up the electronegativity for that atom, for both atoms, and subtract them. So I will have a chart of electronegativities for you. Okay, look at problem number 6. So it says list these elements in order of increasing electronegativity. So we have fluorine in the mix there. So we know fluorine has the greatest electronegativity at 4. So put fluorine over here. So then next would be nitrogen. Okay, so you look, nitrogen is around 3. And then silicon has an electronegativity of 1.8. So that would be next. And then barium has an electronegativity of 0.9. And cesium has an electronegativity of 0.7. Okay, and then let's look at number 7. So it says find the electronegativity difference between each pair of elements and then classify the bonds. So here, boron and fluorine. So fluorine has an electronegativity of 4, boron is 2, so we get a difference of 2, so that would be considered ionic. Chlorine's electronegativity is 3, so we're going to subtract 3 minus 3, and that's 0. Why didn't I put this ionic? This would be nonpolar. And then selenium and oxygen. So oxygen is 3.5, selenium is 2.4. So we'd get a difference of 1.1. So that's in the polar range. And then hydrogen and iodine. Hydrogen is 2.5, iodine 2.1. And we get a difference of 0.4. So that bond is nonpolar. So again, I will give you a table with those electronegativities in them so you have them.